Alright, so we have a function which is integrable and another function which is the same except at finitely many points. We want to show that this new function is integrable and in fact it has the same integral. So this is sort of like the type of question, like you sort of think about why do we want to, like what are the benefits of going about proving these things rigorously, especially like defining integration rigorously. And one of the nice things is that like if you look at a function like this, an arbitrary function where you just change a function at finitely many points, like if you were to just use like standard calculus techniques, like there'd be no way that you'd have any idea of how to do this. So it's really neat that the rigorous definitions of integration allow us to integrate sort of abstract functions like this. But anyways, so g equals f except at finitely many points. So suppose f equals g except at the points x1 through xm. So we're just sort of labeling the points at which f and g are different. Given any particular xi and any delta greater than 0, xi is contained in the union of the rectangles, and we will call them Ri1 through Ri. So let's see here. So this is Ri comma 1. That's the first rectangle, and then we have R. So I'll just call these Rij for now, until we know how many there are. These are of the form. We take the product of I1 through In, where each interval ik is either going to be x. So we take, so xi is an element of Rn, and so we want to take the kth entry. So xi is a particular point, and xik is the kth entry in the element xi. So k, of course, is between 1 and n. So xik minus delta xik, or it could also be xik, then we take xik plus delta. Okay, so what are we really doing here? So a way to visualize this is that if we take a point in R2, let's say that this is our particular x, then we're creating four, let's see here. What we're doing is we're trying to create a neighborhood about this point, and this neighborhood is broken up into rectangles, each of which touches this point at a corner. So we can draw a picture like this and break it up like this. So we've got four rectangles here, and each rectangle touches this point at precisely one of its corners. And if you take the union of these rectangles, then the point is in the interior of that union. So we can label the rectangles. So if we want to figure out how many there are, we have Ri comma 1, and then Ri comma, well, for each n, we have two choices of what for each k between I and n, we have two choices of the interval ik, and so we have 2 to the n choices. So we have 2 to the n total rectangles here. Okay, so note that we also, if we look at the volume of any particular Rij, well, each ik has length delta, and this is a product of direct product of n such intervals, and so the volume is going to be delta multiplied by itself n times, so delta to the n. Okay, so basically what we're going to end up doing, so let's see here, suppose we are given some epsilon greater than 0. So now I'm going to do what I maybe should have started with, but actually show what we're going to do. So we have this rectangle A, and we've got finitely many points x1 through xm in A where f is not equal to g. What we're going to do is we're going to take the function f minus g and try to integrate it. And well, to integrate it, we have to look at partitions. And so we're going to choose a particular partition. What we're going to do is around each one of these points, we're going to sort of make a rectangular grid like we just did. So we'll put a small rectangle here and break it up into further rectangles such that each of these rectangles, one of the corners touches. So we'll do it here as well, do it here as well. Now for this final point I've drawn down here, it's actually on the boundary of A, and so we have to draw rectangles like this, but that's fine. Because we've actually just decreased the number of rectangles we're considering, and so that will actually help our estimate. Because if we integrate the function at these rectangles, we might get non-zero values, but if we integrate it anywhere else, we're going to get 0 values. By the way, I suppose at this point I should mention, we are going to be trying to integrate the function f minus g, or rather g minus f, it doesn't really matter. But once we do that, we're going to use the next exercise. We're going to use the fact that integration is linear in order to finish the proof of this exercise. So technically, it's cheating, but I really think, at least for me personally, it's much easier to think about trying to integrate f minus g versus trying to integrate g. Because if you look at f minus g and you try to actually calculate the upper sums and the lower sums, most of the terms drop out. Okay, so anyways, suppose we're given epsilon greater than 0. Suppose P prime is a partition of A, any partition, and let P be the intersection of P prime with the rectangles Rij, where, so I is going to be between 1 and m, and j is going to be between 1 and 2 to the n. We will denote the resulting rectangles in P by Sij. Then P is a partition of A as well. And in fact, it's a subpartition of P prime. Okay, so let's back up. Some of these things that I've described here are a little hand-wavy. So what we're doing, in order to get this partition P, we start with P prime. And if you look at so you start with P prime, and then you also, wait. hold on. The delta used to define the Rij's must satisfy an inequality. So delta will be greater than 0. It needs to satisfy delta is less than. Okay. This is sort of coming out of nowhere, and the reason I got this is because I worked backwards. MdU1 over n, where d is the largest possible distance between, so this is the max for I over all I between 1 and m of the absolute value of g of xi minus f of xi. And note that d is a positive value and it's finite because there are only finitely many points that we're considering. And that's really key for this exercise. Okay, but anyways, okay, so now that, so this delta was needed in order to define the Rij's, and so that's why I went and defined it. So let's go back a little bit then and figure out like what does P actually look like. Well, we take a partition P prime, and then we consider all these other rectangles, and we want these rectangles or subrectangles to be contained in our new partition. So if we take any rectangle of P prime, and if that rectangle does not intersect any of the Rij's that we've defined, then we just throw it into P. However, if you have a rectangle in P prime which does intersect a particular Rij, then you have to break it up into the part that does intersect the Rij and the part that doesn't intersect the Rij. And then you throw both of those new rectangles into the partition. Okay, so certainly P then is a subpartition of P prime, and furthermore, P contains all of the P contains rectangles Sij, which are all subrectangles of the Rij's. And furthermore, if we look at this picture, it could be possible that some of these rectangles that we've drawn here have been reduced. Like say down here we have, we've got this larger one that was still there, but now in our partition P prime we had a really small rectangle around this point, and so it became like that. So it could have gotten, so some of these Rij's could have gotten smaller, but it's still the case that if you look that these Sij's will each have one of the Xi's at one of the corner points. And if you take a particular Xi and if you look at all the Sij's which share a corner, and you take the union of those Sij's and take its interior, then the Xi will be in that interior. And that's really what we need here. So yeah, a little bit hand wavy, but if you think about it visually, I think it's clear that this can all be defined. All right, so now I claim minus epsilon is less than or equal to L G minus F P, and U G minus F P is less than or equal to epsilon. Okay, so let's prove the first inequality here. So any Sij, here I should probably leave that up. Any Sij so rather any rectangle S in the partition P which is not of the form Sij for any IRJ contains no points at which G is not equal to F. And so, if we take the minimum of G minus F over S, we're taking the minimum of 0 a whole bunch of times, so it's going to be 0. Thus, we have... So now I need to scroll down. Okay, so now, let's see here. So if we look at negative L, G minus F, P, this is the sum over all rectangles S in our partition P. And then we take minus ms G minus F times the volume of S. Now, why do we have a minus sign here? We have a minus sign because we took right, because it's minus L. And L is defined as this positive sum, and so we have this negative sum here. Okay, so we have the sum over all S. And so this includes both S's which are of the form Sij and S's which are of the not of the form Sij. Well, the S's which are not of the form Sij, we know that the ms G minus F is going to be 0. And so the only values that can possibly contribute to this sum are the ones where S is the rectangles S of the form Sij. So we want to take the sum but write it over all Sij. So we take the sum from I equals 1 to m, the sum from j equals 1 to 2 to the n, and now we're going to have minus m, and then we have S, okay. So we have minus m Sij evaluated at G minus F times the volume of Sij. Okay, so now this is going to be less than or equal to, we have the sum from I equals 1 to m again, and the sum from j equals 1 to 2 to the n. Okay, so minus m Sij G minus F. So we take the smallest possible value of G minus F and take its negative. Well, if G equals F, that's going to be 0. However, if G is not equal to F, then it's going to be then it must be some negative value. If G is not equal to F and G minus F is positive, then this value is still going to be 0. However, it could be negative, in which case we subtract it so we get a positive value. And so this G being not equal to F can only happen at the xi's, and the difference between G of xi and F of xi must be less than or equal to D, because D is the largest distance between any gxi and fxi. So this is going to be less than or equal to, we can just put D here, and then the volume of Sij, we've already discussed what that is, and that's just delta to the n. But now these things that we're summing are constants, and so we have m times d times 2 to the n times delta to the n. Okay, but we know that delta is less than 2 to the minus blah 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 blah. So this is going to be less than m times d times 2 to the n times, and now we take this, we use this inequality for delta. So we take 2 to the minus 1, raise that to the n, so that's 2 to the minus n. Then we take epsilon over m d, and this thing in the original inequality was raised to the power of 1 over n, but now here, because we're looking at delta to the n, we raise it to the n, and so the exponents cancel out. So now look, everything cancels out nicely, and this is equal to epsilon. So this is what I did in order to figure out that weird, like, why did I choose delta less than 2 to the minus 1 times epsilon over md to the power of 1 over n? It's because I looked at this thing and I got to this point where I'm like, I have m times d times 2 to the n times delta to the n, and I need this to be less than epsilon. So what condition does that impose on delta? And so I just solved for delta, and I got this. Okay. So that's how we do that. So likewise, if we look at UG minus FP, well, this is just going to be less than epsilon, because it's going to be almost the exact same computation. We're going to get the sum over all rectangles S of capital MS G minus F times the volume of S. And so that's going to be equal to also the sum over all SIJs of capital M Sij G minus F minus volume of Sij. And again, capital M of Sij of G minus F is always going to be less than or equal to D, and so the same inequality from before applies. All right. Thus, so what do we have if we put everything together? We have minus epsilon is less than or equal to the lower sum G minus F P. Now, the lower sum in every rectangle contains a point not in every rectangle in this partition P contains a point which is not one of the xi's. And therefore, the infimum over any rectangle can be at most 0. And therefore, if we take the lower sum, it has to be at most 0. And so this is less than or equal to 0. Similarly, if we look at the upper sum, any rectangle contains a point which is not xi, so every rectangle contains 0. So if we take the supremum, it's going to be at least 0. So 0 is less than or equal to the u of G minus F P, and we've proven that this is less than or equal to epsilon. Okay, so now we're pretty much done, because this is true for any epsilon. So such a P exists for all epsilon, and so then if we take the supremum over all L G minus FP, we know that given any epsilon, we can find a P such that LG minus FP will be greater than or equal to, wait, so I guess this is technically strict. It doesn't need to be strict, but it is. Well, if it's strict, then in particular it's not strict. But anyways, basically you can get as close, by choosing epsilon as small as you want, you can choose a partition that will get you as close to 0 as you want. So if you take the supremum, you're going to be at least 0, because you can get as close to 0 as you want. And you'll never surpass 0, and so it will be 0. And likewise, you can, by choosing a small, fine enough partition P, you can get UG minus FP to be as close to 0 as you want, and it will never be below 0, and so if you take the infimum, you'll get precisely 0. You get infu G minus FP. Thus, G minus F is integrable. I'll use this to denote integrable. It's just integral sign and then BLE. Okay. And because we actually have a formula for what the supremum and infimum are precisely at 0, we have this integral is precisely 0. So by linearity of the integral, which is something that we prove in 3-3b, so this is the part where I'm using the next exercise. We take the integral over all A of G, well, G is equal to G minus F plus F. But now, because of linearity, we can break this up into two separate integrals. We can break this up into the integral of G minus F plus the integral of F. And the integral of G minus F is 0, and so that drops out, and so we're just left with the integral of F. And so if you change a function at finitely many points, then the integral of the function does not change, and the function is still integrable. So this is a really neat result, and it sort of shows you the things that we're able to prove with this rigorous definition. Again, it's not, I guess, a good thing to be using the next exercise to prove this, but this is something that I found most natural, and you can certainly do it without using the next exercise. It's just, I think it's a little easier because a lot of these terms drop out because f minus g is 0 at most points, literally at almost all points in the measure theoretic sense. Whereas if you wanted to prove it without using that, you would have to include a whole bunch of those terms, but explain that that the integrating, that for any rectangle not containing any of the xi's, the integral, or the upper and lower sum of f at that on that rectangle will, or that something on that integral or on that rectangle will be the same for both f and g, because f and g are equal on that rectangle. So it's certainly possible. Another thing about this is this sort of hints at, so if you change the function at finitely many points, the integral does not change. And it turns out that more is true. It turns out that you can change a function at infinitely many points and not change the integral. However, you can only change it at countably infinitely many points. And that's why if you consider the function which is 0 at all irrational points and 1 at all rational points, if you try to integrate this function on any interval, the Riemann integral won't converge because the lower sum will be 0 but the upper sum will be 1. However, if you use measure theory, then you can prove that because there's like way more irrationals than rationals, the integral will actually be 0. But yeah, we're not quite there. So the point is, this is sort of a hint at the types of things that you will be able to prove later on. And in fact, I think we talk about sets of measures here in the next section, but I'm not quite sure how rigorous we go into that, or if we talk about measure theory at all. But anyways, this is how we do this exercise, and so we are done.